All right, recording is rolling. We're back from outside. It's about the last 10 minutes of classic stuff. So let's walk through the answer. What'd you guys get for the height drop of the balcony? About
4.405.
that's sounds about right. About 4.4 something. Right. I'll be 4.4. How about that? Right. Last class I used 4.0. I think it was a little bit over 4 though. Okay, so that looks better. All right. What was one of your horizontal displacements?
9.02.
What was that?
9.02.
9.02 meters. All right, so like 9.0 meters, right? Okay, we're going to calculate the time of fall based on the height of fall. It's calculation. There's only one more measurement to go, right? There are only 4 measurements, and I told you one of. Oh, didn't I have it written on this page? I did tell you guys the mass of the ball, right? Was 0.0064 kilograms. I think I told you guys that. Right, so got that out of the way. We got that measured, boom, boom. The only other measurement was how far was it compressed? Did I do that with you guys too before we walked out?
Yeah.
We got like 0.07 meters if you did all 3 clicks, click. Okay. So we're done with the measurements. Everything else is calculations. Okay, you just do them in order exactly. Let's hear. So first is what is the time of fall? Right, based on the height of fall. So we got our classic H equals 1/2 GT squared. Right? We're trying to figure out what's the time of fall. Okay. Knowing that the height of fall, let's use 4.4 meters. Right? And G, we're using 9.8 meters per second squared. It's T squared. Okay. Now, I do remember if you go to the edge of the cliff and drop a ball and let it fall for 1 second, it falls pretty close to 5 meters. So I bet the time should come out to be a little bit less than 1 second. A little bit less than 1 second. Right. So I'm going to go T squared is 4.4 meters divided by half of 9.8 meters per second squared. Right. And all right, so let's see what that is. That's 4.4 divided by half of 9.8. Right. It's like 0.89, blah, 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 something. Then I have to take the square root. Isn't that true? Take the square root. So T is equal to the square root of point. Extra algebra steps through the peaking. So square root. I'm getting a time of fall of, oh, hey, look, it is a little bit less than 1 second. Wait, 948 seconds. Right. I could really probably say like 0.95 seconds if I knew 2 digits of significance. But since this is a middle step, maybe I'll keep an extra digit of precision and then save more rounding for the end. Right. So we know the time of fall, 0.948 seconds. Right. That's if you have this height. Okay. Now, if you use a different height, then it's okay if your time's a little bit different, but it should be kind of in that ballpark, right? That order of magnitude. Okay. Next step, figure out the blast speed. Now remember where this is coming from. Since you measured how far it went horizontally, and now that we know the time to point, we know those things, we can figure out how fast it was going across the field, which of course is the same thing as blast speed. As long as you aim the cannon horizontally. Right? So let's go D equals BT. Right, this is going to be in the expression. Notice there's no acceleration because there's no acceleration horizontally, but you guys remember that from projectile physics. Okay. So you guys told me 9.02 meters it went. We're solving for how fast it was going across the field, and it had 0.948 seconds to fall. Okay. So you guys see the one algebra step, I'm just going to divide the time over. So the horizontal speed, therefore the blast speed, is it went 9.02 meters in 0.948 seconds, giving you some number of meters per second. Getting 9.51 meters per second. 9.51 meters per second. Okay. Again, that last digit is kind of dubious, but we've still got another calculation to do, so I'll just save it for later. So 9.51 meters per second was going across the field. Therefore, it's been blasted at speed. Right? Okay. And last step to solve for K. But now we're going to switch perspectives, switch frameworks. Okay, so we're done with the projectile stuff. We're going to switch over to the spring itself. Let me cover up that so don't worry about that. Okay. So we got ourselves a conservation of energy at the point of the blast. We're just going from spring potential to kinetic. That's all we're doing. Right. So we're just going to hone in on that right there. Just saw that. Right. And we know all these things except for the K. We know everything else. So I think that's set up. Sum of energy initial equals sum of energy final. Okay. So we got ourselves our point A and our point B, initial final. Okay. So let's go. The energy that was stored in the spring is now turned into energy in motion. Okay. That's our goal. Okay. The spring compression was 0.07 meters. Okay, that's what 7 centimeters is. It's 0.07 meters. Don't forget to square that. Okay. Remember, Hooke's law, the force is proportional to the compression distance, but the energy is proportional to the square of that distance, right? Like the area under F versus that. Okay, and then 1/2 the mass of the ball was 0.0064 kilograms. Okay, and the speed, well, we just did a bunch of projectile physics to figure that out, and we came up with 9.51 meters per second. Or if you have a slightly different number based on a little bit different inputs, that's okay. That should be kind of in that ballpark, should be pretty close to that. This was with 3 clicks, right? So if you only did 1 or 2 clicks, it's gonna be less than that. Okay. All right, you guys good? Okay. Looks like the 1/2 cancels out. I'll just take care of that right here. And K is the mass of the ball times the blast, oh, whoops, kilograms, okay, times the blast speed squared, all divided by the compression of the spring squared. Right? So let's put it all together. Okay. Now, before I hit enter, I think I told you guys before we went out, what did I say a reasonable number would be for a spring constant? I gave you guys a window of values, so between ba and ba. Did I say somewhere between 100 and 200 newton per meter? I think that's what I said, right? So, right, that's what we've been getting all day today. So my earlier classes begin somewhere between 100 and 200 newton per meter. So moment of truth, let's find out. 118, aha, look at there. 118 Newton per meter. Okay, so that looks reasonable. Okay. Of course, you don't have to get exactly that number because everybody had a little bit different numbers or did a little bit different way. Maybe had different balcony height, maybe had a, did a different number of clicks, maybe a little, right? But should be that order of magnitude, should be somewhere there. Okay. That's good. Okay, so we have about 4 minutes of class, which is perfect because here's what we're doing the last 4 minutes. Okay. I need to get you guys your next Open Notes take-home quiz, which is going to be here it is, energy quiz honors. So I'm about to give you guys this right here, Open Notes take-home quiz. This is going to be due on Monday. Here tomorrow when you guys come in, I always write some notes on the projections. I'll write that. I'll say this is going to be due Monday. Okay. This whole lab paper, just turn this in by Friday so I can grade this over the weekend. Okay. Help pace out my grading. But these labs might possibly help you on some of these questions, maybe. So if you think it does, then you're gonna have that paper for reference. So just turn in this whole lab page by Friday, and then turn in the take-home quiz I'm giving you guys right now by Monday. Yeah, I'll go ahead and turn off the squirting, but that is a wrap on today.